Out beyond the known planets, astronomers have long searched for something massive, influencing the outer solar system. But could there really be a hidden planet hundreds of times Earth's scale? Or is the reality something very different? A solar system that doesn't add up. The solar system looks simple when you first learn it. The sun sits in the middle, and everything else moves around it in clean paths. Mercury is close, fast, and hot. Venus is thick and burning. Earth sits in a narrow zone where water can stay liquid. Mars is cold and dusty. Then come the gas giants, Jupiter and Saturn, massive and full of storms and rings. After them are Uranus and Neptune, cold blue worlds far from the sun, moving slowly in wide circles. For a long time, this picture felt complete. It felt settled. A system that made sense under gravity, where every planet had its place and every orbit followed rules that could be calculated. But beyond Neptune, things stop being simple. That is where the system starts to break its clean shape. That is where space stops behaving in a way that matches expectations. Neptune is not the edge, it never was. Beyond it lies a region filled with frozen objects, leftover pieces from the early solar system. These objects are small, icy, and distant. Many of them never come close to the sun. They stay far out in the dark, moving in slow paths that take thousands of years to complete a single orbit. This region is called the Kuiper Belt. It is not a single ring or a neat band. It is more like a wide, messy field of debris that stretches far into space. Inside this region are objects known as trans-Neptunian objects, or TNOs. These are bodies that orbit the Sun beyond Neptune. Some are small, only a few kilometers across. Others are larger, like dwarf planets. Pluto is one of them, but Pluto is only the beginning. There are many more, and new ones are still being found. At first, scientists thought these objects would move in random directions, scattered loosely by the gravity of Neptune and the outer planets over billions of years. That is what the models predicted. That is what the math suggested should happen in a system this old and this wide. But when astronomers started tracking them more carefully, something strange appeared. Instead of being scattered randomly, many of these distant objects were behaving as if something was organizing them. Their orbits were not pointing in all directions. They were grouped. Their paths around the Sun were tilted in similar ways. Even their closest points to the Sun, the points where they swing inward before moving back out, seem to line up in a pattern that should not naturally exist if only the known planets were influencing them. At first, this was not taken seriously. Space observations are messy. Telescopes do not see everything evenly. Some parts of the sky are observed more often than others. Some objects are easier to detect than others, depending on brightness and distance. So the first explanation was simple. It might just be a bias in the data, a trick created by where and how we were looking. But as more objects were discovered, the pattern did not go away. It became stronger. Some of these TNOs were on extremely stretched orbits. Instead of moving in near-circular paths like the planets, they were on long, narrow loops that took them far beyond what Neptune could strongly control. A few of them had orbits that pointed in a similar direction in space, almost as if they were being pulled into alignment by an unseen influence. This is where the problem started to grow. In a normal system controlled by gravity alone from the known planets, these objects should slowly spread out over time. Their orbits should become more random, not more organized. But the opposite seemed to be happening. The more data astronomers collected, the more structure they found in a place that should have been chaotic. The Kuiper Belt itself was not new. It had been predicted long before it was observed. Scientists had expected a belt of leftover material beyond Neptune, formed during the early days of the solar system when planets were still shifting and settling into place. When Pluto was discovered, it was thought to be the first member of this distant region. Later, as better telescopes appeared, more objects were found, confirming that Pluto was not alone. It was part of a much larger population. But what was not expected was structure inside that population. Not just a collection of scattered icy bodies, but signs that their orbits were being shaped in a way that could not be explained by the known planets alone. The idea of orbital clustering became the key focus. This refers to the way several distant objects share similar orbital directions or alignments. Imagine throwing a handful of balls into a large spinning field and expecting them to spread out randomly over time. Instead, they begin to gather into similar paths, moving in a way that suggests once an unseen hand guiding their motion. That is what the data was hinting at in the outer solar system. The more extreme the object, the more unusual its orbit became. Some of these TNOs were not just far out, they were on paths that took them at extreme angles compared to the rest of the solar system. A few even moved in directions that made them stand out completely from the expected orbital plane. In a stable system, this should not happen without a strong reason. Gravity is predictable. That is what makes this problem so important. Every object in the solar system is influenced by the Sun and the planets. If you know their masses and positions, you can calculate how everything should move. That is one of the strongest parts of physics. So when real observations start to disagree with those calculations, it is not something that can be ignored. It means either something is missing from the model or something is wrong with the data. At this stage, scientists began to test every possible explanation. They checked whether Neptune could be responsible. Neptune is massive and already controls much of the outer region. But simulations showed that Neptune alone cannot create the kind of clustering being observed. Its gravity weakens too much at extreme distances. It cannot hold these distant objects in such specific alignment. They also tested whether the combined gravity of many small objects in the Kuiper belt could be enough to shape the orbits. But the total mass of the Kuiper belt is far too small. It does not have enough gravitational strength to organize these objects in such a consistent pattern. They checked whether random chance could explain it. Maybe the sample size was still too small. Maybe more objects would break the pattern. But instead, the opposite happened. Each new discovery added more weight to the same structure. The clustering became harder to dismiss. This is where the central tension began to form. The observations were pointing in one direction, but the known physics of the solar system was not enough to fully explain it. The math did not line up with what was being seen through telescopes. Why do these distant icy objects move the way they do? Not just one or two of them, but a growing group of them spread across a vast region of space, all showing signs of the same hidden influence. At this stage, there is no visual sign of anything massive out there, no direct image, no confirmed object in a telescope frame, only movement, only patterns, only orbital behavior that refuses to fit into the expected model. The solar system, which once looked complete and predictable, now shows a gap in its outer structure, a region where gravity does not behave the way it should if only the known planets are present. The first clues: decades of strange orbits. For a long time, the outer solar system looked like a quiet place that did not change much. After Neptune, there was supposed to be a wide region filled with small icy objects, leftovers from the early formation of planets. Scientists expected it to be messy but simple, a kind of frozen storage zone where objects moved slowly and randomly under weak sunlight and weak gravity. Nothing in that region was expected to behave in a way that would challenge the known structure of the solar system. That was the assumption for decades, and it shaped how telescopes were pointed and how data was interpreted. Then something changed when deeper sky surveys started pushing further out, looking for faint objects far beyond Pluto. These surveys were not just casual scans of the sky. They were careful, long observations using powerful telescopes that could detect very dim reflected light from distant bodies. The goal was simple at first, just to find more objects like Pluto and map the Kuiper belt more clearly. But what they started finding did not fit the expected pattern. One of the first major shocks came with the discovery of a strange object called Sedna. It was not just another distant body. It was something very different from anything seen before in that region. Sedna was extremely far from the Sun, even at its closest point. Most objects in the Kuiper belt stay within a certain distance range, still loosely connected to Neptune's gravity. Sedna did not behave like that. Its orbit stretched far beyond what was considered normal, and its closest approach to the Sun was still far outside the main Kuiper belt region. It spent most of its time in deep space, moving so slowly that it took thousands of years to complete one orbit. At first, Sedna looked like a rare exception. Scientists often expect rare objects when exploring new regions of space. One unusual discovery does not mean the system is broken. It might just be an odd outcome of early solar system chaos. But Sedna was only the beginning. As more surveys continued, more objects with similar extreme orbits began to appear. They were not identical to Sedna, but they shared one important feature. They all moved on very stretched orbits that took them far beyond Neptune's strong influence, and they all behaved in ways that did not match normal expectations. What made things more interesting was not just how far these objects went, but how their orbits were shaped. In a system ruled only by the known planets, distant objects should be scattered in many directions. Their closest points to the Sun, called perihelions, should point randomly in space. This is because over millions of years, gravitational effects from the giant planets should slowly spread their orbital orientations in different directions. That is what models predicted. That is what simulations consistently showed when only known bodies were included. But the real data did not follow that rule. Instead, several of these extreme objects showed a strange kind of alignment. Their perihelions were not scattered randomly. They seemed to cluster in a particular direction in space. This means that when they swing closest to the Sun, they do so from a similar part of the sky. That kind of pattern should not survive in a stable system without a strong organizing force. Over long periods of time, random gravitational nudges should break up any alignment like this. The fact that it was still visible suggested that something was actively maintaining it. At first, this idea was treated with caution. Astronomers know that observational bias can create false patterns. If a telescope is pointed more often in one direction of the sky, it will naturally find more objects in that direction. If detection methods are better in some regions, the data will reflect that imbalance. So the first response was not excitement, but careful skepticism. The question was whether this clustering was real or just an illusion created by how the sky was being observed. For a while, this explanation was enough to slow down any strong conclusions. Researchers pointed out that surveys like these do not cover the entire sky evenly. Some regions are harder to observe because of the Milky Way's brightness. Others are simply less frequently scanned. So it was possible that the clustering was not real, but just a side effect of limited data. But as time went on and more objects were discovered, the pattern did not weaken. It became more noticeable. New objects were not breaking the alignment. Instead, they were adding to it. This is where the situation began to shift from uncertainty to concern. If the pattern was just a bias, then new data should eventually break it apart. Instead, the opposite was happening. The structure seemed to persist no matter how much new information was added. One of the key issues was that these objects were not just clustered in one simple way. There were multiple layers of strange behavior. First, their orbits were extremely elongated, far more than most known objects. Second, their perihelions pointed in similar directions. Third, many of them were tilted in unusual ways compared to the general plane of the solar system. When combined, these features created a structure that was hard to ignore. The Kuiper Belt was supposed to be a wide and messy region, shaped by billions of years of weak gravitational interactions. But instead of pure randomness, astronomers were seeing hints of order inside that chaos, and that order needed an explanation. This is where orbital modeling became important. Scientists started running detailed simulations of the outer solar system, trying to reproduce what was being observed using only known objects. These simulations include the Sun, Jupiter, Saturn, Uranus, Neptune, and a large population of small, icy bodies. The goal is to see if natural gravitational interactions over long periods could produce the strange clustering seen in real data. The result was consistent and clear. Without adding anything new, the simulations could not reproduce the observed patterns. The objects always ended up spreading out too much. Their perihelions did not stay aligned. Their orbital tilts did not match the observed structure. No matter how many variations were tested, the same problem appeared. The known solar system was not enough to create what was being seen. This is a critical point in science, because it means the model is incomplete. It does not mean the data is wrong. It means something is missing from the system being modelled. That missing piece could be a physical object, or it could be something more complex like an unknown gravitational effect, but the simplest explanation usually comes first. At this stage, the idea of an unseen massive object began to enter serious discussion. One of the scientists closely involved in this kind of work was Michael Brown from Caltech. He had already been part of major discoveries in the outer solar system, including the classification changes that led to Pluto being redefined as a dwarf planet. His experience with distant objects and orbital behaviour made him one of the key figures in studying these anomalies. Along with Konstantin Batygin, he began to look deeper into whether a hidden planet could explain the strange orbital structure. The logic was straightforward. If the known planets cannot produce the observed clustering, then something else with significant gravity must be influencing those distant objects. That influence would need to be strong enough to shape orbits over long periods, but distant enough to remain undetected in normal sky surveys. That combination immediately points to a large object far beyond Neptune, moving on a wide and slow orbit. But before jumping to conclusions, the data had to be tested in every possible way. Alessandro Morbidelli and other researchers in orbital dynamics contributed heavily to these investigations. They focused on long-term stability simulations, checking whether the clustering could survive over billions of years under different conditions. These simulations are complex because they track how objects move under gravity across extremely long timescales, adjusting for small effects that build up over time. Even with these advanced models, the problem remained. The clustering of extreme TNOs did not naturally appear unless an external force was introduced. When a hypothetical massive object was added to the simulations, something interesting happened. The orbits of distant objects began to align in a way that looked very similar to what was observed in real data. This was not proof of a new planet, but it was a strong sign that the idea was physically consistent with the observations. What made this situation even more compelling was the slow accumulation of discoveries over time. Sedna was followed by other extreme objects. Each one added another piece to the puzzle. Some had similar perihelion directions, some had similar orbital tilts, some had orbits so stretched that they barely remained connected to the solar system at all. Individually, each object could be explained away as unusual. But together, they formed a pattern that kept repeating. The breakthrough theory. Planet 9 emerges. By the time the strange orbits of the most distant objects in the solar system had been studied for years, the problem had reached a point where it could no longer be treated as a collection of random odd cases. There were too many extreme objects behaving in too similar a way, and the usual explanations were no longer holding up under repeated testing. Observational bias had been checked again and again. Neptune's influence had been modelled in detail. The Kuiper Belt's total mass had been accounted for. Even the idea of pure randomness had been pushed through simulations, and still the same pattern kept appearing in the real sky data. At that stage, the problem shifted from what are we missing in the data to what are we missing in the system itself. That shift is important because it changes the entire direction of investigation. Instead of trying to explain away the pattern, scientists began asking what kind of physical object could create it. And this is where a major breakthrough started to form. Not from a telescope image, but from mathematical behaviour that refused to disappear. In 2016, Konstantin Batygin and Michael Brown at Caltech began to seriously develop a model that could explain the strange clustering of distant objects. This was not based on a new observation of a planet. There was no image, no direct detection, no confirmed signal. It came entirely from orbital mechanics, from the way objects move under gravity when they are influenced over long periods of time. The idea was simple in structure, but very serious in implication. If the orbits of extreme trans-Neptunian objects are being shaped in a consistent way, then something massive must be controlling them from far away. The key point in their work was not just that the clustering existed, but that it had a specific structure. The orbits were not only aligned in direction, but also tilted in a way that suggested a common source of gravitational influence. The pattern was not random and not weak. It was organized enough that it could be modeled mathematically. That meant it was not just a visual coincidence in sky surveys. It was something that could be described using equations. When Bartigan and Brown began testing possible explanations, they ran large-scale simulations of the outer solar system. These simulations included the Sun and all known planets, along with thousands of small icy bodies representing the Kuiper Belt. The goal was to see if the system, as currently known, could naturally produce the observed orbital structure over billions of years. The result was consistent across repeated tests. It did not matter how the initial conditions were adjusted. It did not matter how many objects were included or how long the simulations were run. The clustering of extreme objects did not appear naturally. Instead, the orbits either became too spread out or lost the alignment seen in real data. In other words, the system without anything extra could not reproduce what telescopes were actually showing. This is where the idea of an unseen planet entered the model in a structured way. Instead of guessing randomly, Bartigan and Brown introduced a hypothetical large object into the simulation and tested what would happen if it existed in different positions and with different orbital shapes. The goal was not to prove it existed, but to see if any configuration of a massive distant body could reproduce the real orbital patterns. What they found was striking. When a planet with a mass several times that of Earth was placed on a very distant and elongated orbit, the simulations began to behave differently. The distant icy objects started to organize into patterns that closely resembled the actual observations. Their perihelions began to cluster. Their orbital tilts began to align in a way that matched the real data. The chaotic spread of orbits began to show structure again. This was not treated as discovery. It was treated as a possible explanation that fit the data better than anything else tested so far. But the fact that it worked in simulations was extremely important because it meant the idea was physically consistent with known laws of gravity. Nothing new needed to be invented. No change to physics was required. Only the addition of a single unseen object was enough to reproduce the structure. From this, a set of estimated properties began to form for what this object would need to be if it existed. It would not be small. It would need to have enough mass to influence objects across a vast region of space, far beyond Neptune. The estimates placed it at roughly 5 to 10 times the mass of Earth. This is large enough to be considered a major planet, not a small asteroid or dwarf planet. But it would still be far smaller than gas giants like Neptune or Uranus. Its orbit would also need to be extremely unusual. Instead of moving in a relatively circular path like the inner planets, it would have to move on a highly elliptical orbit. That means its distance from the Sun would change drastically over time, bringing it sometimes closer and sometimes far deeper into the outer solar system. In some models, it could come relatively closer in astronomical terms, still far beyond Neptune, but in other parts of its orbit it could travel hundreds or even over 1,000 astronomical units away from the Sun. This distance is critical to understanding why it has never been seen directly. At such extreme ranges, sunlight becomes incredibly weak. Any light it reflects back toward Earth would be extremely faint. Even powerful telescopes struggle to detect objects at that level of dimness, especially when they move very slowly across the sky. And slow movement is another key factor. Because of its enormous orbit, this hypothetical planet would take thousands of years to complete a single trip around the Sun. That means its motion across the sky would be almost invisible over human timescales. To a telescope, it would not look like a fast-moving planet crossing the sky. It would appear almost fixed in place, drifting so slowly that it could easily be missed in repeated surveys unless astronomers knew exactly where to look. This makes detection extremely difficult because most sky surveys rely on detecting movement over short periods of time. Another reason it has not been seen is simply the size of the search area. The outer solar system is enormous. If a planet is on a long, stretched orbit, it could be located anywhere along that path, which covers a huge volume of space. Even powerful surveys that scan large parts of the sky can miss objects if they are in the wrong region or too faint at the time of observation. So even if such a planet exists, It would not be easy to find just by scanning randomly. There is also the issue of brightness. Unlike gas giants that reflect a lot of sunlight, a distant icy planet would reflect very little. Its surface would likely be dark and cold, possibly covered in frozen methane or other ices that do not reflect light strongly. Combined with its distance, this would make it one of the faintest possible types of large objects in the solar system. This is why the idea of such a planet is not based on direct observation. It is entirely inferred from orbital mechanics. That is an important distinction. In astronomy, not everything is discovered by seeing it directly. Sometimes objects are discovered because of their gravitational effects on other bodies. This has happened before, such as with Neptune itself, which was first predicted due to irregularities in Uranus's orbit before it was ever seen in a telescope. The same principle is being applied here, but at a much more distant and complex scale. Instead of a single planet affecting one orbit, this hypothetical object would be influencing a whole population of distant icy bodies across a vast region of space. The idea is that their unusual clustering is not random and not temporary, but the result of long-term gravitational shaping by something large and unseen. What this planet would actually be like. If this hidden planet is real, it would not look like anything close to the inner planets we know, and it would not behave like the gas giants either, because everything about it is built from indirect evidence, meaning we are not looking at it through a telescope, but instead reading its presence from how other objects move, and that already tells us something important. It is not supposed to be small, it is not supposed to be close, and it is not supposed to behave like a normal planet sitting neatly in the main solar system line. Instead, every model that tries to match the strange orbits of distant icy objects keeps pointing towards something that must be large enough to control motion across huge distances. And that is where the picture of its size begins. When scientists run simulations on the outer solar system, they keep adjusting one thing over and over again: the mass of the object they add to the system, because mass is what decides how strong gravity becomes, and gravity is the only tool that can shape orbits across billions of kilometers. So when they try small values first, like something similar to Pluto or even Earth's moon, nothing changes in the outer orbital patterns. The distant objects still refuse to line up in the way we see in real data, and that tells them right away that the object cannot be small. It must be strong enough to pull on multiple bodies at once, not just one or two passing objects, but a whole scattered population spread across the edge of the solar system. As they increase the mass in the models, something begins to change. Not suddenly, but in a slow and controlled way, where the orbits of these distant icy bodies start responding to the added gravity. Their paths begin to bend slightly. Their closest approach points begin to drift into a shared direction, and their extremely stretched orbits begin to settle into patterns that resemble what telescopes are actually showing. And this is where the estimated size starts to take shape, because the mass needed is not small enough to be a dwarf planet, and not large enough to be a gas giant like Neptune, but something in between that still carries enough force to reshape motion across a wide region of space. The current working range that comes out of these models places this object at roughly 5 to 10 times the mass of Earth, and that number is not chosen randomly. It comes from repeated testing, where anything below that range fails to produce the observed orbital clustering, while anything far above it begins to disturb the solar system too strongly in ways we do not see. So the system itself is acting like a constraint, narrowing down what is possible based on what actually happens in the sky. And this puts the object in a very specific category, something that would be considered a super-Earth in terms of mass, but not a gas giant in structure, which already makes it different from the planets we are familiar with in our own solar system. Now, size alone is not enough to understand what this object would be like, because composition matters just as much, and here the models open up two main ideas that scientists still discuss. The first idea is that it could be an ice giant, similar in broad category to Uranus and Neptune, meaning it would not be mostly rock or metal like Earth, but instead a mix of heavier elements combined with large amounts of frozen gases and ices that formed in the cold outer regions of the early solar system. And in this version, the planet would have a dense core surrounded by layers of compressed ice, water, ammonia, and methane under extreme pressure, creating a structure that is solid in the deep interior, but surrounded by thick fluid-like layers rather than a simple rocky surface. The second idea is that it could be a super-Earth type world, meaning it would be more rocky in nature, built from silicate material and metal, but still much larger than Earth, with enough gravity to hold a thick envelope of gases around it. Not enough to become a full gas giant, but enough to trap hydrogen, helium, or heavier gases that were pulled in during its early formation. And in this version, the planet would have a more solid structure overall, with a deep rocky interior and a thick atmosphere layer sitting above it, making it look very different from ice giants, even though both models still fit within the same gravitational constraints. What makes this debate important is that both versions are still mathematically possible based on current data, because orbital mechanics tells us mass and distance, but not exact surface structure. So scientists are working backwards from gravitational effects, not forward from direct observation, and that means they can narrow down size and position. But composition remains uncertain, because no light from the object has been directly captured in a way that confirms its physical nature. So both ice giant and super-Earth remain open possibilities, depending on how it formed and how it evolved in the early solar system. If we follow the ice giant idea, then this object would likely have formed in the same early period as Uranus and Neptune, when the solar system still had a large amount of gas and dust spread across a wide disk, and planets were still moving around and interacting strongly with each other, sometimes shifting positions before settling into stable orbits. And in that environment, a planet forming far from the Sun would have gathered mostly frozen material, because temperatures were too low for lighter gases to dominate in the same way they did closer in, leading to a structure rich in ices and heavier volatile compounds. And over billions of years, it would have cooled further, becoming an extremely cold and inactive world with a dense interior and a thick outer layer that no longer changes much. If we follow the super-Earth idea instead, then its formation path would be slightly different, possibly involving formation closer to the Sun, followed by a strong gravitational interaction with one of the gas giants, likely Jupiter or Saturn, in the early chaotic phase of solar system development, where planets did not always stay in their current positions. And during these interactions, a large rocky planet could have been pushed outward into the far edges of the solar system, where it became trapped in a wide, stretched orbit, and over time it would have collected a thin atmosphere if conditions allowed. But its main structure would still be dominated by rock and metal rather than thick, icy layers. Both possibilities lead to the same outcome in terms of gravitational behavior, because what matters for the orbital effects we observe is not surface appearance, but total mass and distance from the Sun. And that is why both models can produce similar results when placed into simulations, even though they describe very different physical worlds. The orbital period of this object is one of the most extreme features predicted by these models, because instead of completing an orbit in years or decades like planets closer in, or even centuries like Pluto, this object would take thousands of years to complete a single trip around the Sun, with estimates ranging from about 10,000 years up to 20,000 years, depending on which simulation is used and how its orbit is shaped. And this extreme timescale is not just a detail, it completely changes how the object behaves in space, because it means that for any human observation window, it would barely move at all in the sky. This long orbital period comes from both its distance and its stretched orbit shape, because it does not move in a near circle, but instead in a very elongated path, where it spends most of its time far away from the Sun, moving slowly, almost frozen in motion compared to inner planets, and only during a small portion of its orbit would it move slightly closer, but still far beyond the region of Neptune, and this slow movement is a key reason why it could remain undetected for so long. Because most sky surveys rely on detecting objects that shift position noticeably over short time frames, and this would not behave that way at all. The gravitational pull that creates such a long orbit also explains why it can still influence other objects despite being so far away. Because even at extreme distances, a large enough mass can still shape motion over long periods of time, not by sudden force, but by slow and repeated nudges that accumulate over millions of years, gradually shaping the structure of distant orbits into patterns that reflect its presence, even if the object itself is never directly seen. The moment you move this object out into the region where it is supposed to exist according to every model, you are no longer dealing with a planet that experiences anything like normal sunlight or normal planetary conditions, because at those distances the Sun is no longer a source of warmth or visible energy in any meaningful way. It becomes a distant star that looks almost like a bright point in a very dark sky. And the amount of energy reaching any object out there drops so low that it stops behaving like the planets we are familiar with, and starts behaving like a frozen world locked in deep space conditions that are stable for billions of years without real change. At the predicted distance range of this object, sunlight is reduced to an extremely weak level, not just dimmer than Earth, but millions of times weaker. And that matters because sunlight is what drives temperature, surface activity, and atmospheric behavior. So when that energy almost disappears, the entire environment of the planet changes completely, and what you are left with is a world where heat is not coming from the Sun anymore in any practical sense, but instead from whatever internal energy remains trapped inside it from its formation. And even that is expected to be extremely low after billions of years of cooling. In this region of space, sunlight does not behave like daylight at all. It behaves more like a faint glow that struggles to even reflect off surfaces, so any object sitting there would be covered in near total darkness, not because there is no sun, but because the distance is so large that the intensity of solar energy has dropped below levels that can create visible brightness in any normal sense. And this is one of the main reasons why detection becomes so difficult, because a planet that far away is not only distant, it is almost invisible unless it happens to reflect enough light in just the right direction at just the right time. Temperature follows the same rule, because in space, temperature is controlled mainly by sunlight when there is no strong internal heating source, and once you move far beyond Neptune, the energy input becomes so weak that temperatures drop close to absolute extremes, where most gases freeze and most chemical activity slows down to almost nothing. Meaning that if this object exists, its surface would not be warm enough for liquid anything in normal conditions. And even gases that are common on Earth would exist in frozen or solid form, depending on pressure and composition. At such distances, the temperature would likely sit only a few tens of degrees above absolute zero, which is the lowest possible temperature in physics. And in that state, materials behave very differently from how they behave in warmer environments, because molecules barely move. Chemical reactions slow down almost completely, and the surface becomes a place where time still passes. But physical change is extremely limited, driven only by rare external events like impacts or tiny changes in radiation from space. When comparing this region to known parts of the solar system, the first reference point is Pluto, because Pluto was once considered the outer edge of the solar system before deeper exploration showed that it is actually just the beginning of a much larger region. And even Pluto, which already receives very little sunlight compared to Earth, still exists in a zone where it can occasionally show surface changes driven by seasonal shifts over its long orbit, meaning that it is cold, but not completely isolated from solar influence. This hypothetical planet would sit far beyond Pluto's environment, not just slightly farther, but in a region where even Pluto's weak sunlight becomes significantly stronger by comparison, which means that if Pluto is already a frozen world with ice plains, nitrogen frost, and a thin atmosphere that changes with distance from the Sun, then this object would be a step beyond that state, where even those weak seasonal effects would almost disappear, and the surface would remain in a more constant frozen condition without the same level of variation seen on Pluto. Moving further out, the Kuiper Belt becomes the next comparison, because this is the region where most of the known extreme objects are located, and it is already a zone filled with icy bodies that rarely experience any significant sunlight. But even within the Kuiper Belt, there is still variation, because some objects come closer to the Sun at parts of their orbit and receive slightly more energy, while others stay farther out and remain more permanently frozen. And this variation is what creates the diversity we see in that region. The predicted orbit of this hidden planet takes it beyond the main concentration of the Kuiper Belt for most of its path, meaning that even the average conditions of that region would not apply to it for most of its orbit, because it would spend the majority of its time in areas where the solar energy is even weaker and more spread out, pushing it into conditions that are closer to deep space between star systems than to the structured environment of the outer solar system itself. In that sense, the Kuiper Belt is not the environment of this object, it is only a nearby region that it passes far outside of. And this distance difference matters because it separates a structured population of icy bodies from a single, massive object that exists far beyond their main distribution, interacting with them only through gravity rather than sharing the same space in a meaningful way. Beyond the Kuiper Belt lies the region known as the Oort cloud, which is not a clearly defined structure like a belt, but rather a vast, loosely bound spherical shell of icy objects surrounding the solar system at extreme distances. And while the exact inner edge of the Oort cloud is still uncertain, it is generally thought to begin far beyond the outer Kuiper Belt region, stretching out over distances that can reach thousands or even tens of thousands of astronomical units from the Sun. When comparing the predicted orbit of this planet to the inner edge of the Oort cloud, what becomes important is not whether it reaches into that region, but how close it comes to it at its farthest point, because models suggest that its orbit could extend into ranges that overlap or approach the inner boundary of the Oort cloud, meaning that it sits in a kind of transitional zone between the structured disk-like region of the Kuiper Belt and the more distant spherical cloud of icy bodies that surrounds the entire solar system. This placement is significant because it means the object is not just part of the outer solar system, it sits at a boundary region where the Sun's gravitational influence is already extremely weak, and where passing stars or galactic forces can begin to have noticeable effects over very long timescales. And that makes its environment not just cold, but also dynamically sensitive, even if changes happen slowly across millions of years. How it shapes the solar system. The strange thing about this hidden planet is not just its size or its distance, but what it does to everything around it without ever being seen directly. Because in the outer solar system, where distances are so large and motion is so slow, gravity becomes a long-term shaping force rather than a quick pull. And even a single massive object placed far away can slowly reshape the paths of thousands of smaller bodies over millions of years, without ever touching them or interacting with them in any direct way. And this is exactly what the models show when scientists try to match real observations of distant icy objects with known physics. The first sign of its influence comes from something very specific, which is the way distant objects are grouped in their orbits, not physically close together in space at the same moment, but aligned in the way their paths around the Sun are oriented. And this is important because in a random system, you would expect these orbits to point in all directions after billions of years of gravitational nudges from the known planets. But what is actually observed is that many of these extreme trans-Neptunian objects show a strong tendency to cluster in certain directions, almost as if something is holding their orbital paths in place and preventing them from spreading out evenly. This clustering is not simple or uniform. It appears in different layers, starting with the orientation of their orbits, then extending to the points where they come closest to the Sun, and even to the tilt of those orbits compared to the main plane of the solar system. And when all of these factors are combined, they form a pattern that cannot easily be explained by chance or by the known gravitational influence of the outer planets alone, because over long periods of time, those influences should randomize rather than organize orbital directions. Yet what is seen is a form of organization that keeps appearing even as new objects are discovered. The key idea that emerges from this is that something is acting like a gravitational organizer in the outer solar system, not by pulling objects into a single location, but by slowly shaping the way their orbits evolve over time, guiding their paths into certain stable configurations while preventing them from drifting into completely random orientations. And this kind of behavior is exactly what long-term simulations begin to show when a distant massive object is added into the model. Before introducing that object into simulations, scientists first tested what happens when only the known planets are included, especially Neptune, since Neptune is the dominant gravitational force in that region and has long been considered the main influence on Kuiper belt dynamics. And what these simulations show is that while Neptune is strong enough to scatter objects and create a wide range of orbital paths, it is not strong enough at extreme distances to maintain any kind of long-term alignment or clustering among the most distant objects, because its gravitational influence weakens rapidly as distance increases, and over billions of years its effect becomes more like a background disturbance rather than a shaping force. In these Neptune-only models, the extreme trans-Neptunian objects end up with orbits that become increasingly randomized over time. Their perihelions spread out in different directions, their orbital tilts diverge, and any initial structure that might exist at the beginning of the simulation eventually dissolves, which is exactly what would be expected in a system where no additional organizing force is present, but this does not match what is observed in reality, where the clustering remains present even in objects with extremely distant and elongated orbits. This mismatch between simulation and observation is where the problem becomes serious, because it shows that something is missing from the model, and the missing factor cannot be explained by measurement error alone, since multiple independent surveys have found similar patterns using different instruments and different sky coverage methods, which makes it unlikely that the clustering is just an observational artifact, and instead points toward a real physical influence acting on these objects over very long time scales. When a hypothetical distant planet is introduced into the simulations, something very different begins to happen, because instead of relying only on Neptune's weakening influence, the system now includes a second gravitational source located far beyond Neptune. And even though this object is extremely distant, its mass allows it to exert a slow but persistent gravitational pull on objects that spend most of their time in the outer solar system, and over long periods of time, this pull begins to shape the way their orbits evolve in a very specific direction. The most important effect of this added planet is not immediate changes in position, but slow changes in orbital orientation. Because gravity does not only move objects closer or farther away, it also changes the direction and tilt of their orbits. And in the outer solar system, where motion is extremely slow, even small continuous influences can build up into large changes over millions of years, gradually steering orbital paths into preferred alignments that match what is observed in real data. One of the clearest patterns that emerges in these simulations is the clustering of perihelion directions, where multiple distant objects begin to share similar points in space where they come closest to the Sun. And this happens because the added planet creates a gravitational environment where certain orbital configurations become more stable than others, causing objects that enter this region over long time scales to gradually shift into these stable patterns instead of spreading randomly. Another important effect is the tilt of orbits, also known as inclination, which describes how much an orbit is angled compared to the main plane of the solar system, and in a system with only known planets, these inclinations should become widely distributed over time due to repeated gravitational interactions. But with the added distant planet in the model, the simulations show that certain inclination ranges become more common, while others become less stable, creating a structured distribution that again closely resembles what is actually observed among extreme trans-Neptunian objects. This structuring effect does not happen through sudden changes, but through slow and repeated gravitational nudges, where objects are gradually shifted over long periods of time into regions of orbital space that are more stable under the combined influence of the Sun, Neptune, and the distant planet, And this is why the planet is often described in scientific terms as a gravitational shepherd, because it does not directly collect or capture objects, but instead shapes the environment in which their orbits evolve, guiding their long-term behaviour without direct contact. The scattering of trans-Neptunian objects into extreme paths is another key part of this process, because the outer solar system is not static. It is a region where objects can be slowly pushed into more elongated or tilted orbits through repeated gravitational interactions, and Neptune plays a major role in this scattering process by sending objects outward after close encounters. But Neptune alone cannot explain why some of these scattered objects end up in highly organized orbital clusters instead of completely random distributions, which is where the influence of the distant planet becomes important in simulations. When both Neptune and the hypothetical planet are included in long-term orbital models, the scattering process changes in a subtle but important way, because Neptune still sends objects outward, but the distant planet then acts on those objects over long periods of time, shaping their final orbital configurations and creating patterns in how their paths are distributed, meaning that scattering becomes a two-stage process where Neptune provides the initial push and the distant planet provides long-term structure. Long-term orbital simulations are essential in understanding this process because the timescales involved are extremely large, often spanning millions to billions of years, and in these simulations, small gravitational effects that would seem insignificant over short time periods become extremely important because they accumulate slowly and steadily. And over time, they can completely reshape the architecture of the outer solar system, producing structures that are not visible in short-term observations but become clear when the system is evolved forward over long durations. In these simulations, the presence of the distant planet consistently leads to a more organized outer solar system, where extreme objects do not simply scatter randomly, but instead form patterns in orbital space that remain stable over long periods of time. And these patterns include alignment in orbital direction, clustering of perihelion points, and structured distributions of orbital tilt, all of which match the strange behavior observed in real trans-Neptunian objects. What makes this especially significant is that without this additional gravitational influence, the system naturally trends toward disorder, where repeated interactions between known planets gradually erase any initial structure. But with the added planet, the system develops a kind of long-term stability in specific orbital configurations, not by freezing objects in place, but by continuously guiding their evolution towards certain preferred patterns that persist over time. This is why the idea of a gravitational shepherd becomes central to understanding how this hidden planet shapes the solar system, because it is not acting like a nearby planet that dominates local space. Instead, it is acting from a vast distance, slowly influencing a wide region of space through weak but persistent gravitational effects that only become visible when viewed over extremely long timescales. And those effects are written not in images or direct observations, but in the repeated structure of orbital paths that refuse to behave randomly, despite every known source of gravitational influence already being accounted for. Why we haven't seen it yet. When scientists first started to seriously consider the idea of a large hidden planet far beyond Neptune, one of the first reactions was not excitement, but a very practical question about visibility. Because if something is massive enough to shape the orbits of distant icy objects across the outer solar system, then in normal thinking, it should also be large enough to detect directly. Yet despite decades of searching through deep sky surveys, no confirmed image has ever been found, and the reason for that is not a single limitation, but a combination of extreme physical conditions that work together in a way that makes detection far harder than it sounds at first. The most important factor is sunlight, because every object we detect in the outer solar system is not seen by its own light, but by reflected sunlight, meaning we are always depending on the sun as the original source of visibility. And at extreme distances, that sunlight becomes incredibly weak long before it reaches the object, because light spreads out in all directions as it travels through space, and the farther it goes, the more it spreads, until by the time it reaches hundreds of astronomical units away, its intensity has dropped to a tiny fraction of what it is near Earth. And when that already weak light hits a distant object, only a small portion of it is reflected back toward us, which makes the final signal extremely faint. This faintness is not just a small reduction in brightness, it is a drastic drop that pushes the object into the lowest detectable limits of modern instruments, because telescopes do not just pick up clear bright signals, they also pick up noise from background light, distant galaxies, faint stars, and even internal electronic noise in the detectors themselves. And when a signal becomes too weak, it gets lost in this background noise and becomes almost impossible to separate with certainty, especially when the object is not only faint, but also moving very slowly across the sky. That slow movement is the second major reason why detection becomes so difficult, because most objects in the solar system are discovered by tracking their motion over time, and motion is what separates a nearby solar system object from a distant background star, since stars appear fixed relative to each other over short timescales, while solar system objects shift position slightly from night to night, and this shift is what allows astronomers to identify them in repeated images. But in the case of a planet that is extremely far away and moving on a very long orbital path, the change in position over short periods becomes extremely small, so small that it can easily fall below the detection threshold of standard survey methods. In practical terms, this means that if you take images of the same region of sky over a few nights or even a few weeks, a distant object like this would appear almost stationary, blending into the background of fixed stars. And without noticeable movement, it becomes very difficult to classify it as a solar system object at all, because it does not trigger the usual detection methods that rely on comparing motion across time. This creates a serious problem for discovery, because modern sky surveys are designed around the assumption that objects will move at a detectable rate over relatively short time intervals. So the data processing systems are built to look for changes between images taken hours or days apart, and anything that does not move enough within that time frame can be ignored or filtered out as background noise, meaning that a very slow-moving object could easily be present in the data but not recognized as a moving body. The faintness and slow motion work together in a way that makes the problem even harder, because a brighter object that moves slowly might still be detected due to its strong signal, while a faster-moving object that is slightly brighter might also be detected because its motion makes it stand out. But an object that is both extremely faint and extremely slow becomes almost invisible to standard detection methods, since it fails to meet both the brightness and motion criteria needed to stand out clearly in survey data. Another factor that makes detection difficult is how the brightness of such an object changes, depending on its position in its orbit, because if it follows a highly elliptical path, as models suggest, then its distance from the Sun changes dramatically over time, meaning that at some points in its orbit it could be closer and slightly brighter, while at other points it could be far deeper in space and much fainter. And since we do not know exactly where it is along this orbit, it could currently be in one of its dimmest positions, making it even harder to detect with current instruments. This uncertainty in orbital position creates a wide search problem, because instead of looking for an object in a known location, astronomers have to search across a large region of the sky where the object could possibly be, based on orbital simulations, and this region is not small. It spans a significant portion of the outer sky, meaning that even powerful telescopes can only cover parts of it at a time. And this makes the search more like scanning a vast area under very limited conditions rather than focusing on a specific point. The difficulty is made even greater by the fact that the outer solar system is not evenly distributed in terms of background light, because certain regions of the sky are filled with dense star fields, especially near the plane of the Milky Way, where the number of visible stars increases dramatically. And in these regions, faint objects are much harder to detect because their light is mixed with so many other sources, making it difficult to isolate a weak-moving signal from the background. This means that even if the object is present in a region of the sky that has been observed, it may still be hidden simply because the background is too crowded or too noisy for it to stand out clearly. And this is one of the main reasons why deep sky surveys have not yet confirmed its existence, because detection is not just about pointing a telescope at the right place, but also about having the right conditions for that object to be distinguishable from everything else in the field of view. Another layer of difficulty comes from the way light behaves at such extreme distances, because not all surfaces reflect light equally. And if this object has a dark surface, meaning it absorbs more light than it reflects, then its brightness would be even lower than expected based on size alone. And this would push it further below detection limits, making it even more likely to remain unseen, even if it is relatively large in physical size. When all of these factors combine, faint reflected sunlight, extremely slow motion, uncertain orbital position, background noise from dense star fields, and possible low surface reflectivity, the result is a detection problem that is not just difficult, but fundamentally limited by the current structure of sky surveys. Because even with powerful telescopes, there is only so much sky that can be covered at high sensitivity and high repetition rate, and this creates gaps in coverage where objects can remain undetected simply because they have not been observed enough times under the right conditions. This is where instruments like the Subaru telescope become important in the search, because Subaru has a very wide field of view and strong sensitivity, allowing it to capture deep images of large sections of the sky, which is useful for finding faint, distant objects. And it has already contributed to the discovery of several extreme trans-Neptunian objects that helped build the dataset used to infer the existence of a hidden planet. But even Subaru is limited by observation time and sky coverage, meaning it cannot continuously monitor the entire outer solar system. Pan-STARRS also plays a major role in this search because it is designed to repeatedly scan large portions of the sky and detect moving objects by comparing images taken at different times. And this repeated scanning approach is very effective for finding asteroids and comets within certain brightness and motion ranges. But for extremely distant objects that move very slowly and remain extremely faint, even pan-stars can struggle to clearly identify them, especially if they are located in regions of the sky that are not frequently observed or that contain high background noise. The result of all this is a situation where the object, if it exists, is not hidden by a single problem, but by a combination of overlapping limitations, where each factor on its own might not be enough to prevent detection. But together they create a scenario where even a large planet can remain invisible for a very long time, because it does not announce its presence with brightness or motion in the way most discovered objects do. Instead, it hides in the limits of what current surveys are able to measure reliably. This is why the upcoming Vera C Rubin Observatory is considered so important in this search, because it is designed to address many of these limitations at once by repeatedly scanning the sky with high sensitivity and consistent coverage, building a continuous time-based map of the sky that allows even very slow-moving objects to be detected through long-term comparison. And its ability to capture large areas of the sky frequently increases the chances of catching faint objects that might otherwise be missed in less frequent surveys. Even so, the core difficulty remains the same, because no matter how powerful a telescope becomes, it still has to deal with the fundamental problem of extreme distance, weak reflected light, and slow orbital motion. And these are not problems that can be solved by a single observation or a single instrument. They require long-term accumulation of data across wide regions of the sky. And until the right combination of conditions aligns, the object can remain undetected simply because it does not present itself in a way that matches the detection methods we currently rely on. Telescope survey limitations. The problem does not stop at faint light or slow motion, because even if an object is large enough and reflective enough to be picked up in theory, the way we actually search the sky creates limits that make detection uneven. And this is where telescope surveys themselves become part of the reason why something so important could still remain unseen. Not because the instruments are weak, but because the sky is too large, too uneven, and too complex to be fully covered in a continuous way with the same level of detail everywhere. Modern sky surveys are built around scanning the sky in sections, not all at once, because no telescope can observe every part of the sky at the same time with high sensitivity. So instead, astronomers divide the sky into regions and observe them over time, building a map piece by piece, and this means that some parts of the sky are observed more often, while other parts are only covered occasionally, and some regions are avoided or are harder to observe due to interference from the Milky Way or other background structures. And these differences create natural gaps in coverage that can hide faint objects for long periods. This is not a flaw in design, it is a limitation of scale, because the sky is enormous, and even the most advanced telescopes can only observe a fraction of it in any given night. So surveys must prioritize certain regions based on scientific goals, weather conditions, telescope availability, and observing schedules. And over time, this creates uneven data coverage, where some areas are very well studied and others are less frequently checked. And if a faint, slow-moving object happens to be located in one of those less covered regions, it can remain undetected even if it has been there the entire time. Another issue comes from how data is processed after observation. Because modern surveys do not just take images and look at them manually, they rely heavily on automated systems that compare multiple images to detect changes. And these systems are designed to identify motion by looking for differences between images taken over short time intervals. But if an object moves too slowly, it may not show enough change between images to trigger detection algorithms, and as a result, it can be filtered out or ignored as background noise, even if it is present in the data. This creates a situation where detection is not just about visibility, but also about algorithm sensitivity, meaning that an object must not only be bright enough to be seen, but also dynamic enough to be recognized as moving within the time frame of the survey system. And if it fails either condition, it can be missed even if multiple images of it exist. Blind spots in sky mapping also play a major role in this problem, because the sky is not uniform in observational difficulty. And one of the biggest challenges comes from the plane of the Milky Way, where the density of stars becomes extremely high. And this creates a crowded background that makes it difficult to identify faint moving objects, since they can easily blend into the background of countless other light sources, and in these regions, even powerful telescopes struggle to distinguish weak signals from noise. There are also regions of the sky that are less frequently observed simply due to observational constraints, such as telescope location, seasonal visibility, and competing scientific priorities. And these gaps mean that even if a region contains a potential object, it may not be observed often enough to confirm its motion or brightness pattern. And without repeated observations, it is very difficult to classify an object as part of the solar system rather than a distant background source. Another blind spot comes from timing, because sky surveys operate on schedules, not continuous observation, and this means that there are always gaps in time between observations of the same region, sometimes days, sometimes weeks, and in some cases even longer. And during these gaps, a slow-moving object may not show enough change to be detected, or it may move into a different region that is not immediately re-observed, making it harder to track consistently over time. All of these observational limits combine to create a patchy map of the outer solar system, where some areas are well understood and others are still poorly explored. And this patchiness is important because the predicted location of this hidden planet is not a single fixed point, but a wide region based on orbital simulations, meaning it could be anywhere along a large section of its orbit. And until that region is fully and repeatedly mapped with enough sensitivity, the object can remain hidden simply because it has not been captured clearly in the right observational window. The uncertainty in current location is one of the biggest challenges in the entire search, because unlike planets that were discovered through direct observation or through strong gravitational effects in nearby regions, this object is inferred from subtle patterns in distant objects, meaning scientists do not have a precise coordinate to aim telescopes at. Instead, they have a probability zone, a large section of sky, where the object is more likely to be found based on how it affects other bodies, and this zone is still wide enough that searching it completely requires a huge amount of observational time. This uncertainty is made even more complex by the fact that the object is moving on a very long orbital path, meaning its position changes slowly over time, but still changes enough that its exact location depends heavily on where it is in its orbit at the present moment. And since this orbit can take thousands of years to complete, even small changes in position along that path can shift its location across large areas of the sky from our point of view, making precise prediction difficult without direct observation. In addition to this, the shape of the orbit itself adds another layer of uncertainty, because it is expected to be highly elongated rather than circular, meaning that the object spends most of its time far away from the Sun, moving slowly, and only a small portion of its time closer in, where it moves slightly faster, and depending on where it currently is in this orbit, it could be either slightly more detectable or extremely difficult to detect. And since we do not know its current orbital position, every search must account for a wide range of possibilities. This creates a search problem that is not just about pointing telescopes at the right place, but about covering a large uncertain region over long periods of time, while also dealing with faint signals, slow motion and background noise, and this combination makes the search process extremely demanding in terms of both time and resources. Even with advanced instruments like the Subaru telescope, which has contributed greatly to the discovery of distant solar system objects through deep, wide-field imaging, the challenge remains that it can only observe a portion of the sky at a time. And while it is capable of detecting faint objects, it still depends on repeated observations to confirm motion. And if an object is too slow or too faint in a given observation window, it may not be flagged for further study. Pan-STARRS also adds valuable data to this search by repeatedly scanning large areas of the sky and comparing images over time to detect moving objects, but it still faces the same limitations in sensitivity and coverage, especially when dealing with extremely distant and slow-moving targets, where the changes between observations may be too small to confidently identify motion. The Vera-C. Rubin Observatory is expected to improve this situation significantly because it is designed to repeatedly scan the entire visible sky with high sensitivity and consistent timing, creating a detailed time-based record of how objects change across the sky. And this makes it much better suited for detecting slow-moving faint objects because it does not rely on single short-term comparisons, but on long-term data accumulation that can reveal gradual movement over time. Competing explanations. No planet required? When the idea of a hidden planet was first shaped from the strange orbits of distant icy objects, it did not immediately become accepted as the final answer. Because in science, especially in astronomy, where data is always limited and incomplete, every strong pattern has to survive intense testing from other explanations before it can be considered reliable. And this is exactly what happened here, where the same data that seemed to point toward a large unseen planet was also examined under completely different assumptions that tried to explain the same orbital patterns without adding any new planet at all. The central question driving all of this is simple in wording, but very difficult in structure, because it asks whether the clustering of extreme trans-Neptunian objects is truly caused by a single large gravitational source far beyond Neptune, or whether the same pattern can emerge naturally from known physics, observational limits, and long-term gravitational interactions within the solar system itself. And this question has kept the debate open for years, because both sides rely on real data, real simulations, and real physical principles. The first major alternative explanation focuses on the idea of modified orbital clustering bias, which means that what we are seeing in the data may not be a true physical structure in space, but instead a structure created by how and where we observe the sky. Because every astronomical survey has limits, and those limits can shape what we think we are seeing, especially when the objects being studied are extremely faint and extremely distant, and only a small number of them have been discovered so far compared to the vast number that are believed to exist. In this view, the clustering of distant orbits could be influenced by the fact that telescopes do not scan the entire sky evenly, since some regions are observed more often than others. Some regions are easier to observe due to lower background noise, and some regions are avoided because of interference from the Milky Way or because of seasonal visibility constraints. And when you combine all of these factors, the result is a data set that is uneven in coverage, meaning that the objects we detect may not represent the true distribution of all objects that exist in that region of space. This is important because if observations are biased towards certain parts of the sky, then the orbits of discovered objects may appear to be clustered simply because those are the regions where we are more likely to find them, while other objects in different orbital orientations may exist but remain undiscovered because they are in regions that are less frequently observed. And if that is true, then the apparent clustering could weaken or even disappear as more complete sky surveys are conducted over time. To test this idea, scientists have carefully analysed how survey coverage affects discovery patterns, looking at where telescopes have pointed, how deep those observations go, and how detection sensitivity varies across different parts of the sky. And they then compare this with the orbital distribution of known extreme objects, trying to see whether the clustering could be explained by these observational limits alone, without needing to introduce any new gravitational source. What these studies show is that observational bias does exist, and it does affect which objects are discovered first, because brighter and closer objects are naturally easier to detect, and regions of the sky with lower background noise produce cleaner data. But even after accounting for these biases, the clustering of extreme orbits does not fully disappear, which means that while bias plays a role in shaping the dataset, it does not fully explain the pattern on its own. This leads into a second alternative explanation that focuses not on observation, but on the physical behaviour of the Kuiper belt itself, particularly the idea of self-gravity among Kuiper belt objects, which suggests that instead of a single large unseen planet shaping the orbits of distant objects, the combined gravitational influence of many smaller objects could be enough to slowly organise their orbits over extremely long periods of time. At first glance, this idea seems weak because individual Kuiper belt objects are small compared to planets, and their gravitational pull is extremely weak when considered separately. But the argument here is not about individual objects, but about the collective mass of the entire population. Because even though each object is small, there are many of them spread across a vast region of space, and over long timescales, their combined gravitational effects could potentially influence orbital structures in subtle ways. In this model, instead of a single dominant body shaping the outer solar system, the Kuiper belt itself becomes a distributed gravitational system, where countless small interactions between objects slowly reshape their orbital paths, and over millions or even billions of years, these small effects could accumulate into larger patterns that might resemble clustering when viewed from limited observational data. To explore this idea, scientists run long-term simulations that include large numbers of small bodies interacting with each other gravitationally, along with the known planets, to see whether these combined interactions could naturally produce the observed orbital alignments without requiring any additional massive object. And these simulations are computationally complex because they involve tracking thousands or even millions of small gravitational interactions over extremely long time periods. The results of these simulations show that self-gravity within the Kuiper belt does have some effect on orbital evolution, especially in the early stages of system formation when the distribution of material was denser and interactions were more frequent. But in the current structure of the solar system, where the Kuiper belt is relatively sparse and spread out, the total gravitational influence of these small objects is not strong enough to maintain the specific clustering patterns that are observed in extreme trans-Neptunian objects. What happens instead in most of these models is that self-gravity tends to smooth out distributions over time, rather than create sharp and persistent clustering, because small random interactions between objects gradually spread orbital orientations rather than aligning them into narrow patterns. And this is the opposite of what is observed in the real data, where clustering appears to persist rather than dissolve. However, the idea of self-gravity is still important, because it highlights that the Kuiper belt is not completely empty or inactive. It is a dynamic system with many small interactions happening over long time scales. And while these interactions may not be strong enough to fully explain the observed orbital structure, they can still contribute to shaping the overall distribution of objects in subtle ways, meaning that any complete model of the outer solar system must include these effects alongside any larger gravitational influences. Another important point raised by this alternative view is that the current sample of extreme objects is still relatively small, which means that statistical uncertainty remains a major factor in interpreting the data. Because when you only have a limited number of observed objects, even small changes in how and where they are detected can create patterns that appear significant but may weaken as more objects are discovered in the future. And this is why continued observation is so important in determining whether the clustering is truly physical or partially influenced by sample size limitations. At the same time, even with these uncertainties, the clustering is not random enough to be easily dismissed, because multiple independent surveys using different instruments and different observation strategies have found similar orbital patterns, which reduces the likelihood that the structure is purely an artifact of one specific dataset or one specific method of observation. And this consistency across different sources is what keeps the debate open and active. So at this stage, the situation is not one where a single explanation has replaced another, but rather a case where multiple explanations are being tested against the same data, with each one accounting for some aspects of the observations, but none of them fully explaining everything on their own. And this is where the idea of a hidden planet remains one of the strongest candidates, not because it has been directly observed, but because it provides a single coherent mechanism that can reproduce multiple features of the orbital structure at the same time when included in simulations. Still, the competing explanations serve an important role in keeping the investigation grounded, because they force every aspect of the data to be examined carefully, from how objects are discovered to how they evolve over time under different gravitational influences. And this process ensures that any final conclusion, whether it supports the existence of a hidden planet or not, will be based on a complete understanding of both observational limits and physical dynamics in the outer solar system. Past stellar flyby theory. The debate about a hidden planet does not stay inside one simple idea. Because once scientists saw that the orbits of distant icy objects seemed to follow a pattern, the next step was not to accept one explanation, but to test every possible way that nature could create the same pattern without adding a new planet. And this is where three major ideas became important, each one trying to explain the same data using very different physical processes, and each one coming with its own strengths and limits when tested against real observations and long-term simulations. One of the strongest alternative ideas is the past stellar flyby theory, which suggests that the strange orbital structure of the outer solar system may not have been shaped by something still present today, but instead by a single close encounter with another star in the distant past, when the Sun was still in a crowded environment, possibly inside its birth cluster, where many young stars formed close to each other before slowly drifting apart over time. And in that early environment, the solar system would not have been isolated like it is now, but instead surrounded by other stars moving relatively close in cosmic terms. In this scenario, a passing star could have come close enough to the outer regions of the young solar system to disturb the orbits of icy objects beyond Neptune, pulling some of them into new paths, stretching others into more elongated orbits, and creating a kind of imprint in orbital space that could still be visible today, even after billions of years, because gravitational disturbances at large distances can leave long-lasting effects, especially on loosely bound objects at the edge of a system where the Sun's gravity is already weak. The idea works in principle because stellar encounters are not impossible in the early galaxy environment, and simulations show that a close enough pass by another star could reshape outer solar system populations in a way that might resemble some of the clustering we see today, especially in terms of orbit stretching and inclination changes. But the challenge comes when trying to match the specific patterns seen in extreme trans-Neptunian objects, because the observed clustering is not just about stretched orbits, it is also about consistent directional alignment and persistent structure across different groups of objects. A single stellar flyby tends to create more random distributions of orbital changes, because the gravitational pull of a passing star affects objects differently depending on their position during the encounter, which leads to a wide range of orbital outcomes rather than a focused and consistent pattern. And over time, as the system evolves, these effects tend to spread out rather than remain tightly grouped, which makes it difficult for this explanation to fully reproduce the strong and organized clustering seen in current observations. Another issue with the stellar flyby idea is timing, because if such an event occurred, it would have happened very early in the solar system's history, likely billions of years ago, and over that long timescale, other gravitational influences from the known planets, especially Neptune, would have had time to reshape and randomize many of the initial orbital distortions caused by the encounter, meaning that any original structure left by the flyby would likely be significantly weakened or erased unless it was continuously reinforced by another mechanism. This is why simulations of stellar flybys often show partial matches to some features of the outer solar system, such as extreme orbital stretching or scattered populations, but they struggle to maintain the specific long-term alignment patterns observed in the most distant objects, because those patterns require ongoing influence rather than a one-time event. And this is where the idea of a present-day gravitational source becomes more consistent with the data than a single ancient disturbance. The second major explanation focuses on data sampling bias critique, which goes deeper into how observational data itself might shape our interpretation of orbital patterns. Because every object we know in the outer solar system has been discovered through specific surveys with specific coverage patterns. And this means that what we call the known distribution of objects is not a complete map of everything that exists, but a filtered version shaped by where we have looked and how sensitive our instruments were at the time of observation. In this view, the clustering of extreme orbits could be partly an illusion created by uneven sky coverage, where telescopes have observed certain regions of the sky more thoroughly than others, and where detection limits vary depending on background star density, atmospheric conditions, and instrument sensitivity, all of which affect whether a faint distant object is detected or missed. And when only a small number of extreme objects are known, these observational differences can create patterns that appear more structured than they actually are. The critique becomes more focused when looking at how survey strategies work in practice, because astronomers do not scan the entire sky uniformly. Instead, they target specific regions based on scientific goals, seasonal visibility, and telescope scheduling, which means that some parts of the sky are heavily sampled while others remain less explored. And if the predicted region where a hidden planet might influence objects overlaps with these uneven survey patterns, then the discovered objects could naturally appear clustered simply because that is where the observations were concentrated. To test this idea, researchers carefully reconstruct survey footprints, which are maps of exactly where and how deeply telescopes have observed the sky. And then they compare these footprints with the orbital distribution of known extreme objects to see whether the clustering could be reproduced by observational coverage alone. And while these studies do show that survey bias plays a real role in shaping discovery patterns, especially for faint and distant objects, they still do not fully eliminate the clustering signal seen in the most extreme cases. This means that sampling bias is part of the explanation, but not a complete one. Because even after correcting for known observational gaps and detection limits, the remaining distribution of extreme orbits still shows signs of alignment that are stronger than what would be expected from survey effects alone, which keeps the possibility open that there is an additional physical cause contributing to the pattern beyond just how we observe the sky. The third major alternative idea is disk instability models, which come from thinking about the early solar system when it was still forming from a large rotating disk of gas, dust, and small solid particles, and during that early stage, the environment was much more dynamic than it is today, with frequent collisions, shifting material distributions, and strong gravitational interactions between forming planets and leftover debris. And in such a system, structures can form that are later preserved in the outer regions as the system evolves and cools. In disk instability models, the idea is that instead of needing a single distant planet to shape the current structure of extreme trans-Neptunian objects, the clustering could be a leftover imprint from how material was originally distributed in the protoplanetary disk, where certain regions of the disk had slightly higher densities or different flow patterns that influenced how objects formed and how they were scattered during the early migration of the giant planets. As the giant planets, especially Jupiter and Saturn, moved through the early solar system, their gravitational influence would have been strong enough to reshape large portions of the surrounding disk, scattering material outward and inward. And in this process, it is possible that some regions of the outer disk develop preferred orbital orientations or density structures that later evolved into the populations we see today in the Kuiper Belt and beyond. The challenge with this explanation is that disk instability effects are strongest in the early stages of the solar system, and over billions of years, many of these early structures tend to be erased or significantly altered by ongoing gravitational interactions, especially from Neptune, which continues to influence the outer solar system and scatter objects over long timescales. And when models simulate this long-term evolution, the initial disk structures tend to become more diffuse rather than maintain strong organized clustering in orbital space. Because of this, disk instability models can explain some aspects of the overall distribution of objects in the outer solar system, especially broad features and general populations, but they struggle to reproduce the very specific and persistent clustering seen in the most extreme objects without adding additional forces or constraints, which brings the discussion back to whether an unseen gravitational influence is still required to maintain the observed structure over long periods of time. Across all these alternative explanations, what becomes clear is that each one captures part of the behavior seen in the outer solar system, whether it is early disturbances from passing stars, limitations in how we observe and sample the sky, or leftover structures from the formation of the solar system itself. But none of them on their own fully reproduce the specific combination of orbital clustering, inclination alignment, and long-term stability that is observed in extreme trans-Neptunian objects, and this is why the idea of a distant, unseen planet remains active in scientific discussion, not as a confirmed object, but as a model that continues to match multiple independent features of the data when tested through orbital simulations. The search strategy, how scientists are hunting it. The search for a possible large unseen planet in the outer solar system is one of those scientific efforts where nothing is simple, because there is no confirmed image, no direct measurement, and no spacecraft data pointing to a fixed location, so everything begins from indirect signs, mainly the strange way distant icy objects move in space. And from those motions, scientists try to reconstruct what kind of hidden influence could be shaping them, and then turn that reconstruction into a real search plan that can be tested with telescopes and data systems on Earth. This is not a situation where scientists already know what they are looking at and simply need better tools to see it more clearly. Instead, it is a situation where the target itself is uncertain, meaning the object may or may not exist, and even if it exists, its exact location is unknown. So the entire search process becomes a combination of prediction, probability mapping, and continuous data checking, where every new observation can slightly change the expected region where the object might be found. Modern detection efforts start with the data we already have, which comes from years of sky surveys that have recorded the positions and motions of thousands of distant solar system objects. And among these objects, a small group of extreme trans-Neptunian objects stand out because their orbits do not behave randomly. Instead, they show patterns in their alignment, tilt, and closest approach to the Sun. And these patterns are what originally led scientists to suspect that something large and unseen might be influencing them from far away. Once these patterns were noticed, scientists did not immediately assume a new planet. Instead, they began building computer models of the outer solar system that include all known gravitational forces, especially the Sun and the known planets. And then they tested whether these known forces alone could reproduce the observed orbital structure. And what they found was that while known planets like Neptune can scatter and influence distant objects, they cannot maintain the specific clustering patterns seen in the most extreme cases over long time periods, which suggests that something else might be contributing to the structure. This is where computer simulation narrowing search zones becomes essential, because once the idea of a possible unseen object is introduced into the model, scientists can test different scenarios by changing its mass, orbit shape, distance, and position, and then run long-term simulations that show how the outer solar system would evolve under each scenario. And by comparing these simulated outcomes with real observed data, they can eliminate models that do not match and keep refining the ones that do. These simulations are extremely detailed and require tracking orbital motion over millions or even billions of years in simulated time, because the effects being studied are not immediate but slow and cumulative, meaning that the influence of a distant massive object would not produce sudden changes, but gradual shifts in orbital orientation and clustering over very long timescales. And this makes long-term modelling the only way to understand whether a given scenario is physically possible. As these simulations are refined, a pattern begins to emerge, not just about whether a distant planet could exist, but also about where it could be located if it does exist, because certain orbital configurations produce clustering patterns that match real observations more closely than others. And these successful configurations tend to place the object in a specific range of distances and directions in space, which then becomes the basis for narrowing down the actual search area in the sky. This narrowing process is not precise in the sense of pinpointing a single location. Instead, it produces probability regions, large sections of the sky where the object is more likely to be found based on how well different models match the observed orbital structure. And these regions can then be targeted by telescopes in a more focused way, instead of searching blindly across the entire sky. Once these search regions are defined, sky survey mapping techniques become the main tool for detection, and these techniques rely on repeated imaging of the sky over time, where telescopes take multiple pictures of the same region separated by hours, days, or weeks, and then compare those images to detect any changes in position or brightness, which allows astronomers to identify moving objects among the fixed background of stars and galaxies. The key idea behind sky surveys is that motion is the main signal that separates solar system objects from distant cosmic objects, because stars and galaxies remain fixed relative to each other over short timescales, while objects within the solar system shift position as they orbit the Sun. And this shift can be measured by comparing images taken at different times, allowing astronomers to track movement even when the object is very faint. However, in the case of a very distant and slow-moving object, this method becomes much more difficult because the change in position between observations can be extremely small, sometimes so small that it is close to the limits of measurement accuracy, which means that the object may not be flagged as moving in short-term comparisons and instead requires longer observation periods and more advanced analysis techniques to detect its motion reliably. This is where gravitational modelling refinement becomes important, because as more data is collected on distant objects, scientists continuously update their models of how the outer solar system behaves under different gravitational influences, and each update helps improve predictions of where a hidden object might be located and how it might be affecting observed orbits, which in turn helps refine the search zones used by telescopes. These refined models take into account not only the orbits of known planets, but also the distribution of extreme trans-Neptunian objects, and by comparing simulated orbital evolution with real data, scientists can test whether certain gravitational configurations better explain the observed clustering. And when a model consistently produces better matches, it becomes a stronger candidate for guiding observational searches. In parallel with these physical models, machine learning applied to sky data has become an increasingly important part of the search strategy, because modern sky surveys generate enormous amounts of imaging data that cannot be analysed manually. So automated systems are used to scan images, detect faint objects, and track potential motion patterns across multiple observations. And machine learning systems are especially useful in identifying subtle signals that might otherwise be missed by traditional detection methods. These machine learning systems are trained on known examples of moving objects, background noise, and false detections, and then applied to new survey data to identify potential candidates that match the characteristics of slow-moving distant objects. And while they are not perfect, they help reduce the amount of data that needs to be manually reviewed, allowing scientists to focus on the most promising signals. One of the key advantages of machine learning in this context is its ability to detect patterns over large data sets that might not be obvious in individual images. Because instead of looking at one observation at a time, these systems can analyze long sequences of data and identify subtle, consistent changes that indicate slow movement, even when each individual change is very small and difficult to confirm by eye. Despite these advanced tools, the search still faces major challenges because the predicted object, if it exists, is extremely faint, extremely distant, and extremely slow-moving, which means that even when it appears in survey data, it may not stand out strongly enough to be immediately identified and may require repeated observations and cross-checking with models before it can be confirmed as a real detection rather than noise or background variation. This is why the search strategy relies heavily on combining multiple approaches rather than depending on a single method, because telescope observations provide real data, simulations provide predictive structure, gravitational modelling refines expectations, and machine learning helps process large data sets efficiently. And all of these components work together to gradually narrow down where the object might be located. The Vera C. Rubin Observatory represents the next major step in this search process because it is designed specifically for wide field, repeated sky surveys with high sensitivity, allowing it to scan large portions of the sky regularly and build a time-based map of how objects change over long periods, which is especially useful for detecting slow-moving distant objects that require long observation baselines to confirm motion. Its strength comes from combining depth and repetition, meaning it can detect faint objects while also repeatedly observing the same regions of sky, which increases the chance of identifying slow motion that might otherwise be missed in less frequent surveys. And over time, this creates a continuous data set that is much more effective for tracking long-term changes in the outer solar system. If it exists, what it means for astronomy. If a large unseen planet really exists in the far outer solar system, then the impact of that discovery goes far beyond simply adding another object to a list of planets, because it would force a complete rethink of how the solar system is structured, how it formed, and how stable planetary systems behave over billions of years. And the reason for this is simple but powerful, which is that our current model of the solar system is built on the assumption that we already know the main gravitational players, and if that assumption is wrong, then many parts of modern astronomy would need to be adjusted to fit a more complex reality. The first and most direct consequence would be the expansion of the known boundary of the solar system, because right now the outer edge is often described in terms of the Kuiper belt and the scattered disk, regions filled with icy bodies beyond Neptune that slowly transition into the distant Oort cloud. But if a large planet exists far beyond Neptune, then the structure of this outer region becomes more layered and more complex. Because instead of a smooth transition from dense objects to empty space, there would be a massive gravitational body actively shaping the structure in between, meaning the outer solar system would no longer be seen as a passive leftover region, but as an active, dynamical environment with its own internal organization. This would change how astronomers define the limits of the planetary system, because instead of drawing a simple boundary at Neptune or the Kuiper belt, the solar system would need to include a much larger and more active outer region influenced by this distant planet, and that would push the effective gravitational reach of the solar system much farther than previously thought, since the planet's influence would extend across vast distances, shaping the orbits of smaller bodies and creating structured patterns in regions that were once thought to be relatively random or weakly organized. One of the most important consequences would be a reclassification of solar system architecture, because right now the solar system is divided into clear zones, the inner rocky planets, the outer gas giants, and then the icy outer belt and distant cloud. But the presence of a large distant planet would introduce a new structural layer, one that sits beyond Neptune and acts as a major gravitational organizer for the outermost objects, meaning the solar system would no longer be viewed as a simple layered system, but as a multi-level structure with active interactions extending much farther than previously recognized. This new layer would not just add another planet to the list, it would change how we understand the role of planets in shaping orbital systems, because instead of planets being confined to relatively close distances where their influence is strong and immediate, this object would show that planetary-scale bodies can exist at extreme distances while still maintaining enough gravitational influence to shape entire populations of smaller objects, and this would expand the definition of what a planet does in a system, not just where it exists. Another major consequence would be a shift in planet formation theories, because current models of how planets form are based on the idea that most large planets form relatively close to their star within the protoplanetary disk, where there is enough material density to allow for rapid growth and accumulation, while the outer regions of the disk are usually thought to be too sparse to form large planets easily. So objects beyond Neptune are generally considered to be smaller remnants or scattered bodies rather than fully formed planets. If a large planet is confirmed in the distant outer solar system, then this assumption becomes more complicated, because it would mean either that the planet formed closer to the Sun and was later pushed outward through gravitational interactions with other giant planets, or that planet formation processes in the early solar system were more efficient or more flexible than current models suggest, allowing large bodies to form or survive at much greater distances than previously thought. And both possibilities would require adjustments in how scientists model the early stages of planetary system development. The idea of outward migration would become especially important in this context because one possible explanation for a distant planet is that it formed in a region closer to the gas giants and was later scattered outward by gravitational interactions during a period of early instability, when the giant planets were still adjusting their positions and interacting strongly with surrounding material. And if this is true, then it would provide direct evidence that planetary systems can undergo large-scale rearrangements after their initial formation, with massive objects being moved across vast distances while still remaining gravitationally bound to the system. This would also have implications for exoplanet systems, because astronomers have already observed many planetary systems around other stars that contain large planets in unexpected positions, including gas giants very close to their stars or far from expected formation zones. And if our own solar system also contains a large distant planet that was either formed or moved into an extreme orbit, then it would strengthen the idea that planetary systems are often more dynamically active and less stable in their final configuration than earlier models suggested. In that sense, the discovery of a distant planet in our own system would not be an isolated case, but part of a broader pattern seen across the galaxy, where planets can exist in a wide range of orbital positions, shaped by complex interactions during and after formation. And this would help unify our understanding of planetary system diversity, showing that the solar system is not an exception, but one example of a wider range of possible configurations. Another important consequence would be a deeper understanding of early solar system migration, because current models already suggest that the giant planets, especially Jupiter and Saturn, did not necessarily form in their current positions, but may have moved significantly during the early history of the solar system, reshaping the distribution of smaller bodies as they migrated. And the existence of a distant planet would add another layer to this history, suggesting that the outer solar system may have been even more dynamically active than previously thought, with multiple phases of movement, scattering, and reorganization. In this scenario, the outer solar system would not be a stable leftover region, but a record of past dynamic events where the current distribution of objects is the result of long-term interactions between migrating planets and scattered debris. And the presence of a distant planet would act as a kind of surviving trace of that early chaotic period, still influencing orbital structures even after billions of years, which would make it a key piece of evidence for reconstructing the early evolution of the solar system. It would also change how scientists think about gravitational stability over long timescales, because if a planet can exist at such extreme distances while still maintaining a stable orbit and continuing to influence other objects, then it shows that gravitational systems can remain organized even under very weak solar influence, meaning that stability in planetary systems is not limited to close orbits but can extend far into deep space, where motion is slow and interactions are stretched over extremely long periods of time. This would also affect how future models of solar system evolution are built, because simulations would need to include not just the known planets and smaller bodies, but also the long-term influence of distant, massive objects, which would increase the complexity of modeling outer solar system dynamics and require more detailed long-term simulations to fully understand how such a system evolves over billions of years. In terms of scientific method, the confirmation of such a planet would also demonstrate the power of indirect detection, because unlike most planetary discoveries that rely on direct imaging or spacecraft data, this object would have been inferred entirely from gravitational effects on other bodies, meaning it would represent one of the strongest cases in modern astronomy, where the existence of a major object is established through its influence rather than direct observation, which would strengthen the role of orbital dynamics as a tool for discovering hidden structures in space. Current status, where the mystery stands today. Right now, the idea of a large unseen planet in the outer solar system sits in a very specific place in science, not as a confirmed discovery, not as a rejected idea, but as an active and unresolved scientific problem that continues to be tested from many angles at the same time. And what makes this situation unusual is that both sides of the debate are supported by real data, real simulations, and real observations. But neither side has been able to completely close the case in a final way. On one side, there is still no direct observation of the object, no image that clearly shows a planet moving across the sky in a way that matches predictions, and no spacecraft data or telescope detection that confirms its existence in a direct visual sense. And this absence is important because in astronomy, direct detection is usually the final step that turns a hypothesis into a confirmed object. And without that step, any proposed planet remains in the category of inferred objects rather than confirmed ones. On the other side, there is increasing indirect statistical support coming from the way distant trans-Neptunian objects behave, because their orbits do not appear random when studied in detail, especially those with extremely elongated paths far beyond Neptune. And these objects show patterns in orbital alignment, clustering of closest approach points, and tilt distribution that do not easily match models that include only the known planets. And this mismatch between expected motion and observed motion is what keeps the hypothesis active in scientific discussions. What makes this even more interesting is that these patterns are not based on a single dataset or one small group of objects, because over time, different surveys using different telescopes and different methods have found similar orbital structures among extreme distant objects. And while the total number of these objects is still relatively small compared to other populations in the solar system, the consistency of the pattern across independent observations makes it difficult to dismiss as a simple observational error. At the same time, scientists remain careful in how they interpret this evidence, because the number of known extreme objects is still limited, and small sample sizes can sometimes produce patterns that look more significant than they actually are, especially when detection methods have uneven coverage across the sky. So part of the ongoing work involves constantly updating the dataset as new objects are discovered and refining the statistical models to see whether the clustering remains stable or changes as more data is added. This is why the idea remains actively debated in astrophysics journals, where different research groups publish competing analyses of the same general problem. Some focusing on how a distant planet could naturally explain the orbital structure through long-term gravitational influence, and others focusing on how observational bias or alternative physical processes might produce similar patterns without requiring a new planet. And this back and forth is a normal part of scientific progress when dealing with incomplete data and complex systems. What is clear at this stage is that the search is ongoing and has become more focused over time, because modern sky surveys are not just collecting random data anymore, they are now specifically targeting regions of the sky that simulations suggest are more likely to contain the object if it exists. And this targeted approach is increasing the efficiency of the search by narrowing down the vast space of possibilities into smaller and more probable zones based on gravitational modelling. In practical terms, this means that astronomers are not waiting for a random discovery. They are actively scanning predicted regions using increasingly sensitive instruments, and every new survey adds more information that either supports or refines the existing models, making the search more precise with each iteration, even though no final detection has been made yet. A key part of the current status is understanding what would actually count as confirmation, because unlike many other discoveries in astronomy, where a single image or measurement is enough to confirm an object, in this case, confirmation would require a clear detection of a moving object whose position, brightness, and orbital motion match predictions from gravitational models, and this would likely need to be verified across multiple observations over time to rule out false detections or background confusion. This means that even if a candidate object is found, it would not immediately be accepted as the planet without detailed follow-up observations to track its motion over a significant period, confirm its orbit, and ensure that it behaves consistently with the predicted gravitational influence on distant objects, and only after this full process would it move from candidate status to confirmed planetary object status. At the same time, the role of next-generation telescopes is becoming increasingly important because current instruments, while powerful, still have limitations in sensitivity, sky coverage, and long-term repeated observation. And these limitations make it possible for extremely faint and slow-moving objects to remain undetected even if they are present within the observable range, which is why new systems are being developed to improve both depth and frequency of sky surveys. Among these, wide-field survey telescopes that repeatedly scan large portions of the sky are especially important, because they increase the chances of detecting slow-moving objects by building long-term observational records that allow subtle motion to be identified over extended periods, rather than relying on short-term changes that may be too small to detect in single observation windows. The overall scientific consensus at this point can be described as cautious but open, meaning that there is no confirmed detection but also no complete dismissal of the idea, because the orbital patterns that originally suggested the possibility of a hidden planet continue to appear in updated data sets. And while alternative explanations exist, none of them have yet fully replaced the gravitational model as the most consistent single explanation for all observed features. This is why the situation remains active rather than resolved, because every new discovery of a distant object adds another piece of data to the system, and each piece can either strengthen or slightly adjust the existing models. And over time, this continuous accumulation of data is expected to either confirm the presence of a hidden planet or gradually reduce the need for it as an explanation if the clustering patterns weaken with larger samples. Final sequence. The next stage of this scientific search is not about repeating what has already been done, but about expanding both the volume and quality of observational data. Because the main limitation right now is not theoretical understanding, but the amount of detailed information available about the outer solar system, especially in the region where the predicted object is expected to exist, And increasing that data set is the key to moving from hypothesis to confirmation or rejection. Upcoming observational capabilities are designed specifically to address this gap, with new and upgraded survey systems capable of scanning the sky more frequently, detecting fainter objects, and tracking motion over longer time baselines, which means that objects that were previously too slow or too dim to detect may become visible as data quality improves and observation coverage becomes more complete. These future systems will not just improve sensitivity, but also increase repetition, meaning that the same regions of the sky will be observed again and again over time, which is critical for identifying slow-moving objects in the outer solar system, because motion in that region is so gradual that only long-term comparison of many observations can reveal consistent orbital paths. As this new data begins to accumulate, the expected timeline for confirmation or rejection of the hidden planet hypothesis becomes more realistic, because with enough repeated sky coverage and enough newly discovered extreme objects, the statistical patterns in orbital distribution will either become stronger and more clearly linked to a gravitational source, or begin to fade as the sample size grows and observational biases are reduced. And this will determine whether the hypothesis becomes a confirmed part of solar system structure or is replaced by a different explanation. One of the important possibilities being considered is that the outer solar system may contain more than one unknown large object, because if one distant planet is possible based on orbital patterns, it is also possible that multiple smaller or similarly distant objects could exist, each contributing to the gravitational structure in different ways. And future data may reveal a more complex outer system than a single planet model suggests, with multiple interacting influences shaping the motion of extreme trans-Neptunian objects. As data volume increases, especially from wide field surveys that continuously monitor the sky over long periods, the ability to detect subtle patterns will improve significantly, and this may lead to either a clear detection of a single dominant object or a more distributed model, where several unseen influences together explain the orbital structure, or a complete revision of current assumptions if the clustering pattern weakens under larger data sets. What makes this next phase important is that it moves the problem from limited observation toward data saturation, where enough information will eventually be collected to either confirm a strong gravitational explanation or rule it out. And this transition is expected to happen gradually as more powerful telescopes come online and long-term survey data builds up across multiple years of continuous observation. In this way, the future of the search is not dependent on a single discovery moment, but on a continuous accumulation of evidence, where each new dataset refines the picture of the outer solar system. And over time, this will lead to a much clearer understanding of whether the current orbital patterns require a hidden planet or whether they can be fully explained by known physics combined with improved observational coverage. And until that point is reached, the mystery remains open, actively studied, and central to modern research in planetary science.